Thanks everyone for joining us for today's seminar. The title of today's seminar is DAARWIN, Connecting and Analyzing Data to Reduce Geotechnical Uncertainty. So the bio for the presenter today is Dr. Cristian D. Santos, who is a Master in Geotechnical Engineering, PhD in Soil Mechanics by the Polytechnic University of Catalonia, 2015, and CEO and co-founder of SAALG Geomechanics. He was a junior researcher and consultant for 3 years for the Polytechnic University of Catalonia, 2007 and 2010, and senior researcher and consultant for 6 years from 2010 to 2016 at the same university. Before deciding to create SAALG Geomechanics, an engineering company specialized in advanced numerical solutions, numerical model calibrations, and characterization of soil and rock parameters. He also spent part of his PhD as a visiting researcher at the California Institute of Technology, Caltech, in the USA. He's an expert in finite element software, mainly Plaxis 2D and 3D, and geotechnical back analysis. During his career, he has participated in multiple projects around the world, such as subway lines, high-speed trains, deep shafts, hydraulic tunnels, land reclamation projects, and large buildings with subway levels, among others. Please welcome the presenter today, Dr. Cristian D. Santos.
So, well, thank you for the introduction, and also thank you for the opportunity to be here today presenting part of the work that we have been doing at SAALG Geomechanics. As you can see here, the presentation title is DAARWIN, Reducing Geotechnical Uncertainty by Connecting Numerical Models with Monitoring Data. But also, as you can see, there is a bridge behind. So we like to think about ourselves as a bridge between academia and the industry. Everything that you will see here today is coming from my 8 years and a half doing my PhD at my former university. So basically, after finishing my research with one of my colleagues at university, Ignacy Aligué, the other co-founder of SAALG, we decided to create SAALG as a bridge, as I said, between academia and the industry. Even before starting the presentation, I would like to introduce the company. So we like to say that we are a group of geotechnical engineers as well as software developers delivering digital solutions to help construction to be a more sustainable, efficient, and safer industry by analyzing data during construction. Why? Because we really believe that a better construction is possible, but also because we don't want to be observers of the digital transformation that it's happened at the moment in construction, and we want to be part of this transformation. So that's mainly the reason why we are working every day trying to add something into the construction industry. Even though we are a small team based in Barcelona, we are around 20 people, we have the support of key players of the construction industry like Acciona, one of the biggest Spanish contractor, Cemex, one of the biggest cement companies in the world, as well as Mott MacDonald, one of the biggest engineering firms working in really complex projects. Also, we have the support of public institutions like the European Innovation Council that is supporting our company, as well as helping us to keep developing more technology to transform an industry that is aiming for a transformation. Having said that, also mentioning that since 2016, when we funded the company, we have been involved in more than 40 different projects around the world, working with asset owners, contractors, and designers. So the presentation of today, my idea is first giving an introduction in terms of the problem of geotechnical uncertainty or how geotechnical uncertainty is affecting the industry. I will show the traditional approach as well as our solution. Then I will present a first case study, which is the Girona high-speed train station. It's an underground station near Barcelona with details in terms of the project, the methodology, and the results, and how we implement our solution. Then I will present a second case study, which is a tailing dam. My idea was initially present in detail the tailing dam project, but because of confidential issues, I cannot present everything. So I will be using this excavation case study to present all the methodology and some results, and then I will illustrate with some results the case study for the tailing. And finally, some conclusions and recommendations regarding geotechnical back analysis or how to calibrate numerical models using monitoring data. The reality is nowadays we are capable of building almost everything that we can imagine of. However, those big infrastructure projects, many times or are losing money or we are paying too much for them, both financially, but also environmentally. And part of the reason many times it's because of geotechnical uncertainty, especially during design. Many times we don't really know how the ground is going to behave. And that's making that our designs are overdimensioned. So more steel, more concrete, and at the end, more CO2 emissions. But also this lack in terms of the knowledge how ground is going to behave, it's making that during construction, we suffer unforeseen events causing delays, malfunctioning, and even in the worst case scenario, even the failure of our projects. And just let me put some numbers on geotechnical uncertainty. 1% of the global CO2 emissions are coming just for the additional material that we are expending because of overdimensioning design. And regarding the impact of unforeseen events coming from geotechnical uncertainty, more than 20 billion euros every year in budget deviation, and just taking into account the top 50 European construction companies. So we can say that geotechnical uncertainty is not only a problem for the industry, but also for the society. How the industry traditionally have been tackling this problem, we can say that there are three different approaches, simplifying the problem, but we can say there are three of them. The first one, by increasing ground investigation, especially during pre-design and design stages. So more laboratory tests, more in situ tests with the idea of better characterize the ground conditions. Then, especially during design, we love to use sophisticated numerical tools like the commercial softwares, Plaxis, Midas, Flag, Rock Science suites, that allow us to really simulate complex geometries, complex ground behaviors, and also complex physical phenomena in one software. And then the last approach to reduce geotechnical uncertainty is installing sensors on the ground to monitor the real ground behavior. However, if we take a picture of the entire life cycle of a project, the reality is we are still starting our projects with poor information, that it's making us to use many times unrealistic parameters during designs. And even though we are measuring a lot, we are not really proactively analyzing the data to enrich our models or our designs. If we are lucky enough, we are comparing the data with some kind of thresholds. So we can say that there is a kind of disconnection between the reality coming from our sensors with our predictive models that are our designs. So wasting part of the potential of the numerical tools that we have to be used, that we can use, and also missing the high value of analyzing monitoring data that is available right now, but nobody is proactively analyzing. What we are proposing is a methodology to connect and centralize all the geotechnical information to be analyzed to predict better the ground behavior. The idea is using historical information as well as analyzing monitoring data to enrich our numerical models. How we do that? We do that by using DAARWIN, which is our web platform that we developed based on machine learning algorithms. That the first thing that it does is connecting all the information. Regarding historical information, DAARWIN is a platform that helps us to connect public and private historical information, mainly boreholes, laboratory tests, in situ tests, and all the information required to create our ground models. But also what makes special DAARWIN in terms of historical information is the capability to automate the digitalization of all PDF boreholes. So now in our software, you upload a PDF borehole and DAARWIN read the PDF and give you your digital borehole. Once all the information, this historical information, it's already digital, you can start creating your geotechnical units by analyzing from different boreholes, different in situ tests, laboratory tests, and so on. So basically here you are seeing results from SPT's tests from different boreholes with the aiming to create your ground model to start making your calculations and your predictions. But what really makes different our software is the capability to really connect numerical models with monitoring data to calibrate those models in real time to make better predictions. And this methodology was mainly my PhD, where we integrate and create some new genetic algorithms to increase the speed and the robustness of calibrating numerical models. At the moment, our solution is compatible with the commercial geotechnical software Plaxis 2D and Plaxis 3D, as well as the typical sensors that we have on our construction site, inclinometers, extensometers, piezometers, settlement cells. So basically all the information that we already have available. All the information can be exchanged with Excel spreadsheets, or if the information is stored in other platforms, we can connect our system with third-party systems with no problem. And once the information is in our system, we can first visualize the real response of the ground. What you are seeing here are the horizontal displacements of one of the diaphragm walls of an excavation. But the good thing is now, apart of seeing the data from the sensors, we can actually compare the data with the predictions of a Plaxis model. Here, you can see the dotted lines are the predictions coming from a Plaxis model, a numerical model, based on the design information that we have at the time. And the thin lines with some dots are the actual data from the sensor. So as you can see, we were expecting at the last excavation phase more than 40 millimeters on horizontal displacements, and what we got in reality was less than 20. So basically, we can see here that we were a bit over conservative regarding the stiffness of the ground. And at the end, we were using more material to support the ground in this particular project. But what is really different in terms of Darwin is now we can calibrate the model, especially in the early construction phases. So once you have data, you check the data doesn't match your predictions, you define a back analysis in Darwin using genetic algorithms, which at the end is calculating thousands of different combination of parameters with Plaxis models until we reach to a combination of parameters that allow us to match what we are measuring with the sensors. All those calculations are done on a cloud infrastructure using parallel high-performance computing. Sometimes, even before deciding what geotechnical parameters I want to calibrate, the most difficult question is what are the most influential parameters in my model? Is stiffness, is cohesion, is friction angle, or its permeability? Sometimes it's really difficult to know what is the more influential parameters. So what Darwin also allows you is to do parametrical or sensitivity analysis. So here you are seeing the variation of the response of the model while changing the stiffness, the cohesion, and the friction angle of different layers of the ground in the model. So basically, here you also can control the type of output that you want to see. Here we are seeing bending moments. We can see horizontal displacements. In this case, because it's a structural element, we can see bending moments as well as displacements. And then the idea is you calculate hundreds different numerical models with different parameter values, and then you see the variation of the response of the model. You activate, deactivate different parameters, and you see what are the most influential. But as you can see here, there are many lines, so sometimes it's difficult to know what is more influential. So we create a sensitivity index plot where in an easy way, you can see what are the most influential parameters in your model, as well as when they are more influential. So here it's a key point. We can know what are the most influential parameters that are going to be involved in the back analysis or the calibration once we have data. But what is really important, we know what are the parameters, when we can calibrate the parameters. Not always you can calibrate all the parameters of a model. Just to give you an example, imagine that you want to calibrate the cohesion and the friction angle of a model with data coming from sensors showing you a small displacements. That's going to be almost impossible because we are far from collapse. So cohesion and friction angle have no influence yet in the model. So you are not going to be allowed to calibrate those parameters. So thanks to this sensitivity index, you can see actually what are the parameters that you can calibrate once you have data. Well, that's an overview of geotechnical uncertainty, how geotechnical uncertainty affect our projects, and how back analysis can help us to actually reduce geotechnical uncertainty, and then how Darwin can allow us to automate the process of doing a back analysis. Now I will present the first case study, which is the Girona high-speed train station here in Spain. For the ones that don't know what is Girona, Girona is a city located 80 kilometers north to Barcelona, Spain, with a population almost around 100,000 people. Here are some images of the old town of Girona. In the left, the typical place with the river, the houses, and on the right, the old town with the cathedral behind. The cathedral, quite famous for a TV show, Game of Thrones. I don't know if you are a fan of Game of Thrones, but the stairs are from the Girona Cathedral. The station was built in downtown Girona, surrounded by pre-existing infrastructures. We had already a railway bridge, also historical buildings next to the station. So displacements were something to be aware of. Here are the specs of the station. We are talking about a 600 meters long station, 55 meters wide and 25 meters deep underwater conditions. So it was not easy to build this huge station. The construction procedure was first the diaphragm walls from the exterior as well as the interior diaphragm wall was built before starting the excavation, and then we excavate the whole width of the station at some certain depth, and then we focus on excavating the central part and finally the lateral parts of the station. Here, just some images to illustrate the magnitude of the project. You can see the central corridor combining diaphragm walls panels as well as piles. That's the execution of one of the slabs after the excavation. That's the lowest part of the excavation near one of the extremes of the station, where a TBM was coming from Barcelona to the border of France. Here you can see the TBM. That's the invert of the station. You have to think about that we have more than 25 meters of water pressure, so the structure was really reinforced to support all the water pressure. That's the last excavation part of the station. That's the lateral. It was excavated with 12 meters steps because the results that we were getting from our original numerical models were telling us that the displacements were high. So we had to excavate this last part of the station with 12 meters length steps. We couldn't excavate the 600 meters by one because the model with the original parameters were saying that was not safe. And we will see after all that it was safe actually to excavate the 600 meters because ground conditions were better. But that was what we had at the time during designing. That's the excavation finished, and that's the actual image of the station. The stratigraphy, we have a fill material, an alluvian, and then we have different layers of silty clay and sandy gravel with different stiffnesses. We differentiate between a shallow and a deep material. The majority of the parameters were obtained from pressumeters, but also we have some cross holes and so on. For this model, we were using a hardening soil model as well as morculum from the top materials. The stiffnesses were basically derived from pressumeters, which are the lower stiffnesses that we obtained from our test. We create a Plaxis 2D and a Plaxis 3D. The reason of creating a Plaxis 3D was only to determine the length of the excavation steps in the lateral parts, but the rest of the models were similar while using 2D or 3D. Here you can see the predictions of the original Plaxis model. So we were expecting displacements at the end of excavation 6 around 40 millimeters. What we got that were obtained from inclinometers embedded inside the exterior diaphragm walls was less than 20. So here that's clear what was happening. We assume lower stiffness than what we really had at the time, but that was information. So what we did was a back analysis, was a theoretical exercise. The station was finished when we did our analysis, but we tried to simulate a real process. So we calibrate the model 6 times using data from the first excavation phase, the second excavation phase, the third, the fourth, the fifth, and the sixth. So we reproduce the sequence, the typical sequence that we would have done in a real case study. So basically, first thing that we did was a sensitivity. We determined that the most influential parameters were the stiffness modulus. So we calibrate the different stiffnesses of the different layers. We implement our back analysis methodology, and here you are seeing the adjustment between the monitoring data and the model after the calibration, using data from the first excavation to the last one. The interesting thing that you can see is that the match between prediction and reality, it's good, independently the number or the volume of data that you are using. But what is really interesting is the parameters that we obtain at the end of each back analysis were similar. Imagine that after a new back analysis, you get different parameters. Even though you match the displacements, if the parameters are not constant, you have a problem. That can be because the model is not representing the physics of the problem, or because your monitoring data is not good enough, or you don't have enough data. In this particular case, just with the first back analysis, we had enough information, and the predictions for the future excavation phases were good, and the parameters were constant. So in this particular case, we could change the design or the construction procedure after the first excavation phase. Actually, of course, we check the parameters that we obtained from the back analysis, and the thing was that the parameters that we obtained from our back analysis were closer to the results that we obtained from cross holes, which are a technique to evaluate the stiffness with low range of deformations, which was what we had in our project. So in this particular project, what was the difference of having those bad predictions with displacements around 40 millimeters, or actually having the possibility to know at the end of the first excavation phase that the displacements at the end of the excavation would be closer to 20? So in this case, we could excavate the 600 meters by one, not with the steps of 12 meters length, and that would have saved the contractor more than 2 million euros just by analyzing data that was available at the time, but nobody was using. Well, how we did that in DAARWIN? So, as I said, DAARWIN is a web platform, so you log in. First thing that you do is you edit your project. So basically you define the boundaries of your project. Once your project is edited, you need to upload your design, which is Plaxis models, 2D and 3D. Here you have some images of those models that were uploaded in DAARWIN. Once the models are inside the system, DAARWIN knows all the different calculation phases, constitutive models, and can manipulate the models fully automatically. Here, the 2D. Then you need to define the sensors that you will be using for your analysis and all the comparisons. Once you define the sensors, you can see the icons, where are located those sensors, and then you need to correlate every measurement point with its equivalence in a Plaxis model. So basically, you introduce in DAARWIN the coordinates of the instruments and some references from the model, and DAARWIN select the closest node in your model to be compared with the monitoring data. Next thing that we had to do was defining the construction sequence. So basically, defining all the activities, where those activities were happening, when we start and when we finish, because that allows us to know every day that we have measurements, how was the construction site, and if this situation can be compared with one of the model phases of our predictive models. In reality, every day, many things are happening on the site, but a numerical model is a simplification of the reality. So not all the data can be used to calibrate models. So that's really important, this part. Of course, we allow to put comments, images to make sure that the data they tell you will reach to this point in the excavation. It's true, because sometimes it's really tricky to understand why the sensors are moving, because people are saying, no, we are doing something, and actually they are not doing that. So that's really important, and DAARWIN allows us to know how was the construction site. Then, once we have the model, we define the instruments, we correlate the instruments with the models, and we define the construction sequence. Even before having data, we can see the expected value of each sensor that have been linked to our original design. As you can see here, we are seeing the horizontal displacements expected from one particular inclinometer. And once we have data, you can keep comparing the data with the prediction. Once you see there is a discrepancy, then you decide to calibrate the model. But as I said before, usually the most difficult question to answer is what are the parameters? So you do a sensitivity analysis. How you do a sensitivity analysis? So basically, you select the model in DAARWIN that you want to play with. You define what materials and what parameters you want to play with. You define minimum, maximum, and incremental value. And basically, you will evaluate hundreds of different Plaxis models with different parameter values. Then you have to define what is the output that you want to see. You are interested on seeing displacements, water pressure, or whatever. So you can see what metrics your parameters are affecting. Once you define the parameters and the output, you press calculate, and DAARWIN will start calculating hundreds of different Plaxis models on the cloud fully automatically. And as I showed you before, you will see the different responses of your model. So you will be able to see what are the most influential parameters in this kind of plot, or the other one that I showed you before. In this case, in Girona, we realized that the most influential parameters were the stiffness. So we decided to define the back analysis only trying to calibrate the stiffness. So how we define a back analysis is quite similar to sensitivity. We define what parameters we want to adjust. Then we need to define what data we want to use. So what is the target of the calibration? We want to match displacements, water pressure, or whatever. The user has to decide what are the data that he or she wants to use, as well as what parameters you want to calibrate. DAARWIN is not telling you what are the parameters that you need to calculate. DAARWIN is a tool for engineers to be used to calculate hundreds and thousands different models. Then you press calculate, and then you start using our genetic algorithms that, among billions of different possible combinations, after evaluating some thousands different values, obtain a combination good enough to match what we are measuring on the site. So the results that you see is a table with the original parameters, the optimal one, some statistical values to see the quality of the results. And then you can plot all together the data with the calibrated model. And as well, you can add, if you want, the original design to see the difference. But at the end, what we do in SAALG is creating this technology to allow engineers to calibrate their models during construction to impact the project. And that was coming from a PhD creating algorithms and also automating the process to adjust a Plaxis model and connect the Plaxis model with monitoring data. Also, not only you can see the optimal value, you can see all the 1,000 Plaxis models that you have been evaluating, you can actually plot all together in the system. Okay, I will go to some slides regarding the tailing just to give you an idea the type of results that we can get by doing a back analysis and a sensitivity in a tailing dam project. So basically, here you can see different Plaxis models from different projects, from different tailings. I'm showing some of them because I cannot actually show you the one that we use for this particular project. But again, you define the geometry and the rising of the tailing. So here, what you are seeing is the comparison between the original Plaxis model and the monitoring data. In this case, you are seeing the comparison between the water level inside the tailing during the raising of the tailing. So as you can see on the bottom right side with many colors, the orange line is the actual water pressure coming from a piezometer, and those black dots are the actual prediction of the water pressure coming from the original design. As you can see, there is a discrepancy. Then we also analyze the difference between the settlements during the raising between the data and the original Plaxis model. As you can see, we were measuring higher settlements than what we expect from our original Plaxis model. So first thing, we ran a sensitivity to check the influence of permeability and stiffness of these models in terms of water pressure as well as settlements. So here you can see how the water pressure can fluctuate if you change stiffness and water pressure, and permeability. Actually, the influential parameters in terms of water pressure was basically permeability. As you can see here, the plot, the orange bar is showing permeability of this particular material was the most influential, with 70% of the influence. Also, we did the same for settlements. So here it was a combined influence between permeability, because it was a consolidation analysis, and stiffness. That's why now you can see that the influence is shared between the orange bar and the blue line on the bottom. Then we decided to calibrate permeability and stiffness of different materials in the model. And here are some of the results. So actually, you can see the original design, the optimized design, and the monitoring data. In terms of water pressure, you can see that we match, or we are closer to the actual measurements, but not only in water pressure, we also match the displacements that we were measuring. So in this case, we proved that we could adjust displacements and water pressure by calibrating the stiffness and the permeability of different materials using different types of data. Just to conclude, some ideas or recommendations regarding geotechnical back analysis. The first one is back analysis is really a powerful methodology to calibrate numerical models in early construction stages with the idea of validating the hypothesis using design, detect instabilities in advance, and finally, it's opening us the possibility to optimize the design and the construction procedure even during construction. However, it's extremely important to check that the numerical model is representing the physics of the problem, because there is a really nice expression, rubbish in, rubbish out. So we need to make sure that even though our original model is not predicting the displacements, but we need to check that the model is reproducing the behavior of the problem. The similar thing is with the monitoring data. We need to make sure that the data is good in quality, but also that we have enough information to make our analysis. And also, that seems obvious, but it's extremely important to have a clear visibility what was happening on the site the day that we had data. Because sometimes, and especially from my experience, I spend most of my time doing calibrations, trying to figure out how was the construction site the day that I had data. So that's really important. And actually, that's something that we focus when developing this technology, to make sure that we make it easy to connect design, construction, and data, to make sure that then we can analyze something. And finally, this idea that even though you have fancy tools, you can recalibrate models, make better predictions. If you want to really impact a project by updating ground conditions and reducing whatever element you want, you need to make sure that all the different stakeholders are aligned. So the owner, the contractor, and the designer. If not, that's impossible. So it's better to plan in advance a conservative design of different design options. You agree all the different options depending on different geotechnical situations, and then once you have data, you decide, let's go for option B, C, or whatever. But that's really important. And that was more or less what I was intending to present today. So if there is any question or comment, I would like to try to answer all of them. So thank you very much.
Thank you, Doctor. Is there any questions from the room here? Give me a sec.
Thank you, Dr. Santos, for your great presentation. I have some quick questions for you. So you were also talking about the numerical modeling for the site characterizations and the big projects.
I cannot hear you well. I don't know if you can go closer to the mic.
Can you hear me now?
Yeah, a bit better, not a lot better, but yes.
Yeah, I think it might be better.
How about now? Is it better?
Okay, let's try it.
Yeah, okay. You were mostly focused on the site characterization and how numerical modeling, like with DAARWIN, can be used for like site characterization and these big projects. How about like small projects like lab tests? Can we use like DAARWIN for numerical modeling of the lab tests, like innovative lab tests? Do you think that's a possibility?
Well, actually, this functionality is already available in Plaxis, so you can try to adjust some laboratory tests. The thing is, yes, you can do that in DAARWIN, so you reproduce your laboratory tests in Plaxis, then you get all the data and put all this data in the system, and that's all. But there are similar things already implemented in Plaxis, but yes, you can do that if you want. Not sure if Plaxis allowed you to introduce your data, but I'm guessing you can introduce the data from a laboratory test in some way.
Is it just compatible with the Plaxis, or is it compatible with the iTask software package as well?
So at the moment, we are just compatible with Plaxis. Our idea is for the future to be compatible with other software like Rock Science, Flag, or Midas. But yes, at the moment, we are only compatible with Plaxis.
Yeah, thank you for that. And just another quick question. Is there any trial versions of the DAARWIN that we could try, or is there any educational license for that?
Yes, we actually have a kind of a free trial for 3 months. And also we are collaborating with some universities. So there is the kind of educational or university license. But the easiest way is you reach to us from our web and you ask for this free trial, which are 3 months.
Oh, I see. Thank you very much. Let me see if there is any questions in the...
I have a quick question, please. This is Mahir from WSP USA. So is this DAARWIN platform only for Europe, or it's also available in US?
Actually, we are working in US in some projects. So there is no limitation. We are working Japan, Singapore, North America, in Latin America. So there is no limitation. Actually, we are working with some of your colleagues in UK, but we are happy to have more people using DAARWIN. So no limitations in terms of locations.
And for the help resources, is there like available training or documents to guide us step by step how to use this platform?
Yes, so actually how we usually work, so our idea is to be a software provider, even though at the moment, many times we do the implementation, we use the software by ourselves to the end client. But what we are doing with designers, especially, there is a training plan. So we train the designers to make sure that they can use DAARWIN by themselves. There is a tutorial, a step by step. So at the end, you will be fully autonomous to use DAARWIN by yourself.
Thanks. And when do you think this platform can be used by another software, for example, RS2 from Rock Science?
Okay, to be honest, it's not one of our priority at the moment, so I cannot tell you when. So what is easier for us in some projects that they don't have Plaxis, we actually encourage the client to create a Plaxis model based on the other software, or actually we recreate a Plaxis model from the original software.
Thanks.
There are some questions in the chat box that I'm gonna read them for you.
In fact, if you want, I can just, I'll read it out loud too.
Yeah, that would be great, actually.
Yeah.
Yeah.
Christian is Chris Kellen from the Sequent Geotechnical Group, so Plaxis and GeoStudio. Great presentation. Just wondering, over the course of the last couple of years, have you found design consultants to be quite receptive to changing their design while a project is in progress? Or is there a lot of, that conservative nature of most engineers? Do you see some pushback there, or pretty receptive?
Okay, here there is a thing, and basically designers are willing to be using this kind of technology because they know that better designs are possible. So they actually are pushing to this direction. However, the reality is they are supporting liability in many of the projects. So liability is an issue. So all the changes that you are proposing, sometimes they are getting the liability, but they are not getting the benefit of reducing material, going faster. So that's a problem. What we are seeing is in those projects with design and build contracts, designers are more willing to take the risk because there are some benefits for them. But I think that here our challenge, and I think it's similar for designer, is not a technological challenge, it's more a contractual challenge that actually they promote you to do better engineering, but there are something in return. So yes, I think that designers, engineering firms are willing to use these kind of solutions to be more involved and deliver leaner and better designs.
Great, thank you. Yeah, that makes really good sense. Thanks.
You're welcome.
Yeah, there is one more question in the chat box that says, for the back analysis in the DAARWIN, is the DAARWIN reaching out to Plaxis to run the different scenarios and find the best fit to monitoring data? Is that the way that DAARWIN is doing it?
Yeah, so the process, because our optimization algorithm are genetic algorithm, the method basically is, in our case, we start like calculating 200 Plaxis models that have been randomly generated. We calculate the models, we extract the results, and we evaluate the error between the model and the measurements. Then we apply some genetic algorithms operators to change those parameters from those randomly generated models to get a better models that are closer to the solution. So we keep iterating until the algorithm find a family of solutions that are good enough. So basically, we are evaluating with 200 Plaxis models each step. So at the end, we are evaluating thousands, like 5,000 Plaxis models in 6-7 hours, depending on the size of the Plaxis model that we are using in the project.
Thank you very much.
But the system is, every calculation is using 200 virtual machines with 200 Plaxis license.
Okay, thank you very much for your answer. And that's it for the chat box. Is anyone in the room has any questions? Like, is there anyone? No? Okay, no questions anymore, apparently. So thank you very much for your time and just for your great presentation. And yeah, I think that's where we stop the presentation. Thank you.
Thank you.
Perfect. Have a good day.